Hello, today we are going to discuss our next lecture, which actually we will discuss in brief that about the doping applications on various methods, or maybe that using of doping for various applications. So mainly we have kept our lecture title like this, that modified nanomaterials in use for consumer products. So that means whatever the products we are going to use, say suppose for the electronics purposes, for the sensing purposes, for maybe some solar cell technology, or maybe for biomedical applications, then how this doping material can be introduced, can be used for these particular applications. So first we are starting our applications on doping based on the electrocatalysis techniques. That means on electrocatalysis techniques, that how these doping materials is giving some better results, or maybe rather we can say that how these doping materials is influencing the electrocatalysis applications. So when we are talking about the electrocatalysis, first that increased world energy need has focused requirement of new solutions to balance energy demand, because when we are talking about some kind of electrocatalysis materials, always we are trying to keep in mind that how we can increase the energy density at that particular material, because every material is having certain limitations. So our main motto is that our material should be less expensive, should be cheap, should be less weight, but it will store the more energy at that particular time. So same thing when we are talking about the fuel cells is nothing but some kind of, it is coming under some kind of renewable energy. So renewable energy means we are not hampering the environment, it is one kind of green technology where we can make certain materials which can absorb the maximum energy at that particular point, and later when we need those energy, easily we can extract that energy from that particular material and we can use that energy for our day to day life. So here when we are talking about this electrocatalysis mechanisms or fuel cells, say suppose some kind of graphene materials, generally that nitrogen doped graphene we are trying to utilize for this particular purpose, which is giving the better properties or maybe the some enhanced properties in terms of fuel cells and the electrocatalysis techniques. So what we are going to show you, that N doped graphene exhibits high catalytic efficiency accompanied by enhanced stability and better carbon monoxide and methanol tolerance compared to the previously used platinum based cathodes. So when we are using this kind of materials, so previously we are using some materials which is generating the carbon monoxides, or maybe which is generating some kind of methanol inside the system, maybe that material can't sustain, or maybe some kind of toxic gases can come from the that particular techniques which can create some kind of hazardness to the environment. So nowadays we are trying to use this nitrogen doped graphene which can be readily made in our laboratory and which can tolerate this kind of carbon monoxide gas or maybe some kind of toxic gases which is generating inside the systems so easily, so that this material can be used for a longer time. Also, a high local spin densities on the graphene basal plane leads to increase the adsorption kinetics of oxygen and oxygen reaction efficiency. That means simultaneously it is increasing the adsorption technology. Adsorption is nothing but the attachment of the gas molecules on the substrate surface itself, it is not going inside. So that absorption of the oxygen also, this kind of material is increasing, so that we can get some better properties. Next we are trying to discuss this kind of doping materials on based of some electrochemical energy storage, mainly for the batteries and the supercapacitors. If we remember that nowadays every time we are talking about the lithium ion battery, or maybe we are trying to discuss about the supercapacitors, which is nothing but the some kind of energy storage device. That means when I am generating this energy, so I have to store this energy in somehow, because when I need it or maybe at the time of power cut, I have to use this kind of energy. So for this purpose I have to make certain kind of storage tank which can absorb this energy, and when I need it easily I can take out the energy from that particular material. So that means this kind of materials is nothing but a one kind of energy absorber. So when we are talking about this kind of materials, people are also trying to use this kind of doping materials or maybe the modified nanofillers for enhancing their storage capability. So we are talking about the lithium ion battery. In the anodes side. So 3-dimensional stacked BC3 sheets provide a capacity of 857 milliampere hour per gram, which is 2.3 times greater than that of graphite. So what I am trying to tell in this particular case, that when we are using this graphite, it was giving the 372 milliampere hour per gram, but when I am using this boron carbide, then sheets have been the capacity has been increased, it has gone up to 857, which is nothing but the twice or maybe thrice of this graphitic value. Then sometimes we are using the reduced graphene oxides, then that sheets also doped with boron. That means this RGO we are doping by the boron, means boron doped RGO material through the exposure of boron bromide shows a high capacitance, that is 1549 milliampere hour at 50 milliampere per G charge discharge rate, better than similar nitrogen doped materials, which is giving only 1043 milliampere hour per gram. So almost the results is 1.5 times better than the previous one. So in that particular case, what we are trying to say, that when we are trying to modify these materials from the surface itself, or maybe the atomically, or maybe we are using some kind of dopant or impurities inside it, the material electrochemical properties is totally changing. And not only that, here also that boron doped materials tested as anode materials for lithium ion batteries, so shown discharge capacity of 548 milliampere hour per gram at 100 milliampere per G after 30 cycles. This indicated 2 times improvement compared to the pristine graphene. So here also we are trying to pretend the same thing, that when we are trying to utilize those materials, the total material electrochemical properties or maybe the energy storage properties is increasing tremendously. Same thing we are showing in this particular graphs also. So here we are having the graphs irrespective of potential versus the capacity. So here we have shown that when you are doing for the first cycle, then 5th cycle, 10th cycle, 20th cycle, that means we are trying to load this kind of energy for several cycle. That means we are giving the energy to that particular systems for a certain time, then we are trying to discharge the energy from that particular system, and then we are trying to see that how much energy it is absorbing, then how much energy it is discharging, and then for how much long period it is discharging the energy. So nowadays one important parameter I am going to tell you, that when we are using some kind of iPad or maybe iPod or maybe the laptops or maybe the mobiles, our main motto is that when we are charging these instruments, that charging should be very fast, but discharging should be very less or maybe the very slow process. So same thing here also we are trying to do, that we are charging these materials for a short time, but discharging should be less, so that I can use or maybe utilize this energy for the longer time. Same thing in this particular case also we are trying to use. Here it is the some kind of applications, that where we are having the anode electrode, in the one is the negative electrode, one is the positive electrode, that means one is the cathode, one is the anode, then I am charging it. In between that I am having some electrolyte separator or maybe that electrolyte membrane, which will allow that one positive ion to go from one side to another, but it should not be reversible. So by this way we can do the modification of this kind of materials. Next we are trying to discuss about the supercapacitors. So supercapacitors is also one kind of energy storage device, but that is for the shorter time. But still what we are trying to do, we are trying to modify these supercapacitor materials so that it can store more energy than the previous one. So in that particular case also we are trying to dope the RGO, reduced graphene oxide, which is remarkable electrical conductivity about 44 Siemens per centimeter, and the specific capacitance is coming 448 farad per gram in 6.0 mole KOH. So I am using certain kind of electrolyte solutions. Same thing we are having two electrode, one is cathode, one is anode. Then I am trying to store the energy inside that material. This technology can be used for the supercapacitor applications, maybe some batteries or maybe the lithium ion batteries, where I am using one anode materials as a lithium. So here also we can see that boron doped materials exhibit specific capacitance of 172.5 farad per gram at 0.5 ampere per gram, which was maintained almost constant 96.5% after 5000 cycles. That means the longevity of that particular material, or maybe that life of that particular material, has been enhanced. So when I am charging that materials and discharging that materials for several times, still the capacity of that particular material is remain same. That means that battery life, or maybe the supercapacitor life, is increasing, so that I can use this material for a longer period. Also, boron content showed the best performance overall with respect to pristine graphene 4% weight, and with boron doped materials show a capacitance improvement of 86%. So, just you see that when we are using the simple boron in, or maybe the pristine graphene, that percentage is coming around 4%, but when we are using these boron doped materials, its capacitance improvement is more than 86%. At 3% doping of boron, excellent surface area like 622 meter square per gram of doped graphene was observed. At 1 ampere per gram, the specific capacitance was 281 farad per gram, which was maintained very stable even after 4000 cycles. So when we are collecting all these results, just we are trying to establish that when we are trying to dope this kind of materials, when we are trying to improve this kind of materials by any kind of doping, or maybe that surface wrappings, or maybe the coatings, the property, electrochemical property of that particular material is increased tremendously. Same thing we are showing over here also, when we are using that IV curve of that particular materials, that current density versus potential, here we are showing the charging, and here we are showing the discharging. So that means when I am giving the energy of that particular material, how much energy it is being absorbed by that particular material, how much energy it is depositing inside it, and then how fast or how slow this material is releasing the energy. Same thing we can see that when we are going for a different scan rate versus the specific capacitance at that particular material, we have seen that doped reduced graphene oxide properties has been increased tremendously. Same thing we have shown for the different cycle number and versus capacitance graphs also. So here in this particular case, that our boron doped, or maybe that doped graphene oxide has overcome, or maybe that has totally suppressed the results of pristine graphene oxides. Then next topic is that we can use this kind of materials for the sensing applications. So sensing means, as I told in my some previous lectures also, we can use this kind of sensors for the various applications, whether we can use this kind of materials for the gas sensor, maybe some kind of light sensor, maybe some kind of distance sensor, or maybe sensing any kind of materials where maybe that human body, or maybe that human being can't reach, or maybe can't go at that particular point, or maybe can't trace some kind of trapped materials over there, some kind of toxic materials over there. So nowadays the making the sensor with this kind of materials is a tremendous challenging jobs. When we are talking for detecting a particular gas, maybe it may be easy, but when we are talking to detect some kind of dual gases, or maybe mixing of several gases, really that task is still challenging. So people are trying to use this kind of materials for the dual gas applications, or maybe some kind of toxic gases applications, where we can easily detect this kind of materials, or maybe this kind of gases very easily without the intervention of any kind of human being. So here also the dopants efficiently combine intrinsic electric and electrochemical properties of graphene with chemical activity. So here generally different types of sensor we are going to use. First one is called the gas sensor for the gas sensing applications, optical sensor for optical sensing applications, electrochemical sensor for electrochemical sensing applications. Multifunctional system detects different analyte selectivity even in ppb, which is nothing but the parts per billion range. That means the main motto of this particular study is that detection limit should be very high. Suppose in a particular room or maybe particular area a very little amount of gas or maybe any kind of toxic gases are present, my sensor material should be capable enough that that can easily detect those kind of materials so easily. So, when we are talking about particular about the gas sensors, so generally there are two types of gas sensors we can use. One is called the resistive type sensors, another one is called the chemical type sensors. So, when we are talking about the resistive type sensors, so a resistive gas sensors have large changes in the electrical conductance after the exposure of two target molecules such as ammonia as a donor and the nitrogen dioxide as the acceptor. So, for pure graphene the sensitivity of the doped device is 27 and 105 times higher for nitrogen dioxide and ammonia respectively. So, here just we are going to show you that we are using two types of gases, one is the ammonia or maybe the ammonia environment, another one is the nitrogen dioxide or maybe the nitrogen dioxide environment. So, in this particular case both are almost the toxic gases. So, in this particular case what we are trying to do, we are trying to make our sensor so that easily it can detect this kind of gases. So, what we are trying to do over here? So, when we are talking about the pristine graphene, that we are trying to measure the current versus time in this particular case, and pristine graphene also we are using for the detection of nitrogen dioxide and detection of the ammonia gases. So, what we are trying to show that once we are trying to make the material without any doping. So, simple we are using these materials as a film or maybe as a powder or maybe as a some kind of devices, simply we are keeping into these two environment, then we are creating some kind of potential difference in between that and we are trying to measure the resistance of that particular material. Then same material or maybe the same sensor, then I am doing the modifications like this kind of doping, maybe some kind of boron doped or maybe lithium doped or maybe some kind of wrapping or maybe some kind of coatings. Then after modifying these materials, then again I am putting into the same environment and just I am trying to show that how the resistance of that particular material is going to be changed. So, whatever the resistance it is changing, it is actually depend upon the volume and concentration of that particular gas. So, if we train our sensor materials in such a manner, if I know that particular resistance will come for that particular gases, so when I am using this kind of sensing materials into some particular environment, if my material will show the same current or maybe the same resistance at that particular point, so that we can say that for that particular current or maybe the resistance, this gas is present at that particular time. So, this is the actually whole logic behind this technology. So, when we are talking about the doped nanoribbons, so here doped nanoribbons also all another type of latest kind of materials which we are using nowadays for the detection of some kind of toxic gases or maybe detection of some kind of sensing materials. So, here is the scanning tunneling microscope images that demonstrate the nitrogen oxide molecules adsorbed on substitutional boron atoms at the center of the nanoribbons, thus nanostructures works as Lewis acids. So, here in this particular case when we are using the boron doped graphene, generally we know that boron doped graphene is a one kind of substitutional doping. So, boron is going to the substitutional side on that graphene sheets and then it is trying to adsorb, that means that nitrogen dioxide gas has been trapped on the surface of that boron doped nanoribbons and its absorption property is going to be increased. Same thing it is happening in this particular case also, ammonia gas also the absorption property is increasing, so that the more ammonia gas or maybe the more nitrogen dioxide gas can be adsorbed for these particular doping materials. Then also these kind of doping materials we can use for the optical sensor purposes also. So, here the phenyl boronic functionalized graphene oxides is used as an efficient glucose sensor. So, generally this kind of sensors we are going to use for the biomedical applications or maybe a detection of some kind of glucose, sugar or for the human body. So, the device selectivity relies on the strong affinity of borates for diol groups in the presence of glucose. So, this is the main logic of this particular doping technology. Since boronic acid has higher affinity, thus the probe is displaced and the fluorescence recovered. Detection of glucose from 25 to 75 milligram per milliliter is done. So, in this particular case actually what we are trying to do, we are trying to modify this kind of nanofillers, and then I am trying to use this kind of nanofillers for the glucose monitor. So, here also the same thing, that we are measuring that that glucose detections at different PL versus PL intensity versus the wavelength, and just we are trying to measure that how much light actually it is absorbing, and then if it is showing some kind of color or not, and then how its wavelength is changing, so that by changing the wavelength we can easily detect that how much percentage of glucose is present at that particular system. Same thing by doing this kind of techniques also we can measure that what is the concentration of that glucose for that particular systems, and also sometimes we are using some doped GQDs. GQDs is nothing but the graphene quantum dots. So, this is also one kind of modified materials. Nowadays it is also having several good properties, and also it is making or maybe it can be possible to make this kind of materials in our lab. So, what we are trying to make, we are trying to make this kind of materials. Not only that, we are trying to dope this kind of materials so that its sensing property can be increased. So, here the doped GQDs used as sensing agents for the aluminum ion. Increase in the photoluminescence property. What is the advantage of using this kind of materials? It is increasing the photoluminescence property of that particular material. Sensor shows good linearity between the optical response and the aluminum 3 plus ions concentration. Very good detection limit of 3.6 millimole is being used in this particular case. So, here you can see that fluorescence microscopy image. So, when we are putting this kind of material under the fluorescence microscope, so it is showing some kind of light at that particular case. So, if we can see that when we are trying to increase the concentrations also, so automatically the light reflecting properties of that particular material is also changing. So, by showing this kind of image, also not only that, when we are taking the intensity versus wavelength, we can see that at different intensity or maybe the same wavelength, the intensity of that particular material is changing. Rather we can say that at different intensity is wavelength also can be changed. But in that particular case, by getting this kind of fluorescence microscopy results and the PL emission spectra, we can easily detect that what is the percentage of that particular metal ion into that systems, and then how it is behaving, or maybe the it's changing its sensing properties. Then this kind of materials we can use for the electrochemical sensor applications also. So, here the doped graphene simultaneously detected the hydroquinone and the catechol. So, these all are the different kind of materials. By doping only the graphene, we can sense this kind of materials for the electrochemical purposes. So, here in this particular case, that superior electrocatalytic activity compared to pristine graphene towards the redox reactions of hydroquinone and catechol having detection limits 0.3 millimole and 0.2 millimole respectively. So, here just we are trying to show that when we are using this kind of doped materials, how our sensing properties is changing, or maybe how our sensing properties is increasing. So, in the right hand side figure, just we have shown some kind of FESM image. So, where we are showing the structure of that pristine graphene, rather we can say that morphological structure of that pristine graphene, and when we are doing this boron doped graphene, that how the crystal structure that morphological structure is changing. Not only that, in the below picture you can see that size of the flakes has been increased, that means it is showing certain kind of porous structure, that means it can absorb some kind of gases, so that it can increase the sensing properties of that particular material. Here also the same thing, here just we are trying to show that boron doped graphene nanosheets, where you can see that boron particles has been substituted substitute the carbon atoms at that, or maybe the boron atoms has been substituted the carbon atoms. That means in this particular case we are trying to show that boron is the substitutional, actually boron doped graphene is the substitutional doping method of boron into the carbon structure. And here also we are trying to show you the charge discharge cycle. So, how the material is sensing the materials and then how it is releasing and coming back to its original positions. Here the boron graphite electrode was used to detect the H2O2 hydrogen peroxide by monitoring the electrocatalytic reduction current at minus 0.4 volt versus silver and silver chloride solutions. Excellent sensitivity of electrode 367 microampere per millimole per centimeter square versus means which is more than the 258 microampere per millimole per centimeter square for non-doped graphene. So, from this particular case you can see that how the sensitivity properties of that particular materials is increasing from 258 to 367. Not only that, the good detection limit of around 3.8 millimole. So, overall the sensing property of that particular material has been changed tremendously by using the boron doped graphene, electrode. Next, we can use this kind of doping material for the photovoltaics applications, or maybe rather we can say for the solar cell applications, or maybe some kind of energy storage devices. So, here the doped graphite or maybe the doped graphene silicon based solar cell exhibits very good properties. Short circuit current density of 18.8 milliampere per centimeter square and a fill factor of 22.8% has been observed by doping this kind of materials. So, here also where we are trying to show that how the current density is changing with the difference in between the voltage, or maybe when we are putting some kind of potential difference in that particular systems, and not only that how the total current density is changing. So, here one is for the pristine one, another one is for the doped graphite silicon based solar cells. So, here also what we are trying to show that few layer graphene with 1% boron doping used as back electrode in cadmium tellurium based solar cells, the increased conductivity and the hole collecting ability of boron graphene allowed to obtain better performance with respect to both pristine graphene and the reduced graphene oxides. So, graphene oxide, if you remember that graphene oxide, first we are making it from the graphite itself, then when we are trying to remove some kind of functional groups from it, that is known as the reduced graphene oxides, and the graphene is nothing but the removing or maybe removal of all functional groups from it, and its layer may be one layer or maybe two layer or maybe three layer. So, that is why it is called the few layer graphene sheets. So, here this is the cadmium tellurium solar cells, which is nothing but the making it by the layer by layer techniques. So, first we are having some kind of glass, then we are using the FTO over there, then on top of that we are putting the cadmium sulphide on top of that, then we are trying to put the graphene, and not only that, this kind of materials we are putting for the using for the photovoltaics applications. And then from when we are using this kind of things, so you can see that when we are increasing the voltage and the current density, you can see that boron doped graphene is giving the maximum performance at that particular level or maybe at that particular conditions. So, here the short circuit current for boron graphene reached a value of 21.96 milliampere per centimeter square. So, you can see that how the short circuit current is reaching only doping by the boron for this particular material. So, these kind of materials we can use for the biomedical applications, maybe for the biosensors, or maybe some kind of biological applications, or maybe some kind of biomedical applications. So, here what we are trying to see that HeLa cells can be incubated with boron graphene quantum dots for 24 hours without significant loss of viability. That means the whatever the material or maybe whatever medicines we are trying to make, what is our main motto? Our main motto is that when I am swallowing any kind of tablets or medicines or maybe the capsules inside our body should accept this kind of materials, or maybe I am trying to put certain kind of implants like some elbow implants or maybe some kind of knee implants into our body. So, what the type of material generally we are choosing? We are trying to choose certain kind of materials which can be compatible with the bone structure. Not only that, easily our blood or maybe our cells can take that or that body or maybe that accept our that material so easily, so that there should not be any toxicity or maybe any kind of deteriorations inside our body. So, here what we are trying to do, that we are trying to modify this kind of graphene quantum dots doped by the boron, and we are trying to use this kind of materials for the biomedical applications. So, here what we are trying to show is that absorptions in terms of that simple graphene quantum dots and the boron doped graphene quantum dots, where we can see that absorption spectra for the boron graphene quantum dots has been increased tremendously. Not only that, when we are trying to characterize our material in terms of intensity versus the wavelength, we are showing that boron graphene quantum dots is showing a particular level, it is increasing its intensity. That means this material is much better than the graphene quantum dots. Not only that, here we have tested the viability of HeLa cells with an incubation time of 12 hours, and where we are trying to change the concentration level of boron graphene quantum dots, and here is the cell viability. That means when I am preparing certain kind of materials, I am putting that materials in contact with some cells, then what we are trying to see, that at what time how many cells are alive or maybe how many cells are going to be died. So, in that particular case, just we are trying to see that how much or maybe that how many cells has been died or maybe deteriorated, or maybe there is no deterioration or maybe any kind of cell dieness is not taking place, so that our cells has easily accepted these foreign materials. So, by choosing this one, we are trying to see the cell viability test of that particular cells. Here what we are trying to show, that when we are increasing the concentrations also, still the cell viability is still not deteriorating, it is into the same level. That means this material is, first of all, it is not toxic. Our body can readily accept these materials does not have any kind of side effects, so that the cell can easily alive inside the systems or maybe on the surface of that particular material. Not only that, boron graphite quantum dots obtained by microwave synthesis process, generally by this process we have made this kind of doping of this particular graphene quantum dots, and here a standard MTT assay confirmed low cytotoxicity of boron graphene quantum dots, 87% cell viability after 12 hours incubations with 4.0 milligram per milliliter of boron graphene quantum dots. That means when I am increasing the percentage of that particular doping material inside these cell systems, still our 87% cells are alive. That means I can use this kind of materials for some future biomedical applications, say for some kind of implants or maybe some kind of lenses, maybe some kind of stents, so that it can enhance the mechanical properties of that particular material, maybe some other important parameters for that particular material, but it will not hamper or maybe deteriorate our body systems. Not only that, it is not going to generate any kind of toxic gas or maybe toxic material, so that our blood or maybe our cells can die or maybe that can change its properties. So, that materials is very acceptable to the human systems. Then we are trying to tell this kind of materials in terms of functionalizations. Till whatever the discussions we are doing, that based on the doping, But now what we are trying to do, we are functionalize this kind of nanofillers, and just we are going to see that where we can use or maybe where we can utilize this kind of materials for better performance. So first we are trying to use this kind of functionalized materials for the molecular junctions cases. So the electrical characteristics of photochromic molecules are explored by embedding them in between two electrodes in a molecular junctions. So that is the basic principle, that how we are going to use this kind of materials. The electrical characteristics of these junctions is governed by the structure and energetics of the two components, and their interfaces also by the ability of the chosen molecule to transport the charges. So here same thing, we are trying to use different electrodes over there, then in between the electrodes total electrochemical reactions is going on, and we are going to see that how this material is performing inside that system. So when we are talking this kind of materials, so here one thing, we are trying to use some kind of materials which can make the bridges in between the carbon nanotubes. That means that electrolytic materials or maybe some kind of in between materials, whatever that can be readily be acceptable by both the electrode. Same thing we can see here in that particular case also, that azobenzene bridge is forming in between these two materials. So here the bridge two CNTs with a dirilethene molecules, here also the bridging is taking place with two graphene point contacts with a azobenzene molecules. So this material is readily acceptable by both the electrodes. So that is why we are getting the better properties when we are using this kind of materials for the molecular junctions. Then the bridging of two CNTs with a dirilethene molecules occurs via amide formations, and carbon nanotubes point contacts are made by electron beam lithography. So by electron beam, applying the electron beam lithography techniques, we are attaching these two carbon nanotubes by this kind of materials. Same, the thiophene based devices show only one way switching from open to closed state. Same thing, we are trying to use this kind of functional materials for the field effect transistors, or maybe in short terms we know it as a FETs. So FETs based on spiropyran functionalized carbon nanotubes could be switched from high to low conductance. So that is the one problem over there. Then light driven reversible doping of graphene by pyrene substitutes azobenzenes. So these kind of materials, by doing this kind of modifications or maybe the functionalizations, we can enhance the electrical properties of that particular material. Not only that, the charge carrier concentrations, which is the vital parameter for the FETs, is modulated by ultraviolet and white light illuminations by plus minus 1 into 10 to the power 12 per centimeter square, preserving charge carrier mobilities of pristine graphene. Then also the how the azobenzenes without pyrene groups directly deposited on graphene, the E isomer modified graphene shows stronger doping effect than that of Z isomer due to the molecular conformation change. So by this way, this material is, we are trying to modify that this material can be used for the FETs. Then we can use this kind of material for the solar thermal storage applications, or maybe for the solar energy applications. So effective conversions of light into heat is an emerging area showing great potential in solar thermal storage, because nowadays when we are using this kind of coal or maybe the petroleum or maybe the thermal power plant, so always we need some kind of energy. So we have to charge the energy from the coal into the electrical energy, but storage of this material is very limited. Maybe next few years we can finish all our coal, or maybe that water can be dried out. So anything can be possible. So what we are trying to do, we are trying to use certain materials which can easily readily available from the environment itself. Not only that, the sunlight will remain same for a longer time. So why we are not using this sunlight, and we can convert this sunlight into the electrical energy systems. So same principle we are trying to utilize in this particular case. So here also we are trying to make certain kind of bridges in between the CNTs. Not only that, we are trying to make certain kind of materials which can easily absorb the energy from the sun and convert that energy into the electrical energy. Not only that, after generating this electrical energy, we have to store this energy for a longer time, and when there will be any power cut or maybe we need some power, easily we can access that power very easily. Not only that, some kind of optimized intermolecular hydrogen bonding interactions and increased functionalization degree improves both the storage capacity and the lifetime. So, here also we are trying to utilize some kind of materials, and we are trying to functionalize these materials by the hydrogen functionalizations or maybe the hydrogen bonding interactions, so that its storage capacity or maybe that lifetime of that particular material can be increased. What is the results obtained from this particular study? Energy density up to 138 watt per hour per kg, long term storage half life exceeding 1 month, excellent cycle stability for the 50 cycles. That means the stability of that particular material is increasing, so that I can use that material for a longer time. Not only that, when I will store that energy in that particular material, also the discharge time will be increased. Not only that, the material can store the same energy or maybe same amount of energy for a longer time itself. Then we can use this kind of materials for the memory devices. So, that is also one kind of technology, like we are trying to use some kind of CD, DVD, some kind of USB pen drive, or maybe some kind of memory devices. If you remember, when we are using first time at the computer, our hard disk was so big, because our memory devices was so big that it was very difficult to bring that memory device from one room to another. But nowadays we are using simple 1 terabyte memory devices or maybe the storage systems in a pen drive itself. So, how our storage capacity is increasing, but still we are reducing the size of that particular storage capacity or maybe that storage materials. Not only that, it should be lightweight, it should be less expensive, and not only that, it can be easily made. So, here a typical rewritable memory behavior with an I on and I off ratio of 20 and a retention time exceeding 10 to the power 4 seconds, which is due to the resistive switching of the azobenzene monolayer. So, here we are trying to functionalize this kind of materials by the azobenzene. The non-volatile memory exhibits stability exceeding 400 cycles of write, read, erase, read. So, here generally previous time when you are using some kind of CD, we are only that CD is having that capability that it can write, or maybe we can write some materials inside that, but we can't delete it. But nowadays whatever the storage systems we are going to use, simply we can erase it, we can delete those materials, then again we can store some kind of materials. So, that is the read, write, or maybe erase, every facility can be possible for that particular systems. Not only that, these devices also show good memory characteristics under bending stress, demonstrating their potential use in flexible electronic devices. So, I can use this kind of materials for certain purposes, where maybe some mechanical load or maybe some mechanical pressure can be applied, but still the material will not damage. Also, voltage controlled non-volatile molecular memory device by using an azobenzene monolayer as the active layer sandwiched between two reduced graphene oxide electrodes can be possible. So, here what we are trying to show, that we are trying to put certain kind of functionalized groups on these particular materials, so that its memory or maybe that its storage capability is increasing. Not only that, when you are talking about the current intensity in terms of time, so one is the off time, another one is the on time, then we can see that how the material properties is changing and how its storage capability is increasing. Thus, we are calling it as a voltage controlled non-volatile molecular memory device. So, by these methods or maybe by this way, we can make this kind of materials. Next, we can use this kind of materials for simple sensing applications. So, what we are trying to do? We are trying to make certain kind of materials which can detect the color, because sensing the gas or maybe sensing some kind of thermal properties or maybe that heat or maybe some kind of distance may be easy, but when that material is detecting some kind of color, really this is a very challenging job. So, what we are trying to do? We are trying to do that a nanoscale color detector based on carbon nanotubes modified with azobenzenes, where the azobenzene serves as photoabsorber and the nanotube as the electronic readout. So, here we are trying to modify our carbon nanotubes by the azobenzene, which is increasing its which is increasing its color detectorness or maybe the color sensing properties. Also, the amidation reaction to chemically graft pyrons of carbon nanotubes and used such as a hybrid system to regulate the horseradish peroxidase activity via light irradiations. The enhancement in the catalytic HRP activity has been used as a level free calorimetric assay of lysozyme with a detection limit of 30 nanomolecule or maybe that nanomole. So, here what we are trying to use, that we are trying to use the sensing properties of that material, that so that it can detect the color. We can use this kind of materials for the sensing applications, or for, say we can use this kind of materials for the biomedical applications too. Next, some kind of for particular biological applications also we can use this kind of materials. When we are using this kind of materials, before going to say something about this slide, just I am telling that here two terms has been written, one is called the in vitro, another one is called the in vivo. So, in vitro is nothing but when we are doing or preparing this kind of materials and we are testing these materials inside our lab. But when we are injecting this kind of materials into some mice or maybe some rabbits, that is called the in vitro applications. So, one is called the in vivo, another one is called the in vitro. So, in vitro is nothing but the we are testing inside our lab with some cells or maybe some kind of characterizations we are doing. In vivo, simple same thing, same materials we are putting to see that how that animal is reacting or maybe the how that medicines or that particular material is working. So, here the photochromic molecules have been used to modulate a number of important biological process such as protein folding, enzyme activity, membrane transport and so on. Carbon based nanomaterials are also widely employed for biomedical imaging, drug delivery and the cancer therapy. Nowadays, so many people are working on the targeted drug delivery. The main function of this kind of materials is that directly I can apply this kind of medicines or material to the affected zone. It will not go to the unaffected zone. That side effects of these particular materials is going to be reduced, and not only that, from that outside simply I can locate that how the material is going on to the affected zone, how the medicine is working on the affected zone. So, these all are the added advantage of using this kind of materials. Not only that, photochromic carbon based nanomaterials are capable of responding to a light input and behave as active building blocks for biological applications such as fluorescent probe for diagnosis and drug carrier in drug delivery systems. So, here what we are trying to show you, that I am when I am using some kind of materials, I am putting maybe I am doing or maybe I am using these materials for the laboratory purpose and I am putting this kind of materials into some mice. But when I am exposing these materials into the UV light, simply from the outside I can detect that where the material is lying, how the material is behaving and then how the material is changing its characteristics. So, by this wonderful techniques we can easily detect some kind of tumor cells or maybe some kind we can remedy some kind of tumor cells or cancer cells inside our body. So, now we have come to the last part of this particular lecture, which is nothing but the summary of this whole lecture. So, here boron doped graphene represents only one among the large family of heteroatoms doped graphene, with whom it shares many interesting properties. Already we have discussed the boron doped graphene for numerous applications. A more delicate design via incorporating enhanced components combining photochromic molecules with carbon based nanomaterials is needed to realize the control motion of a surface. The design of well defined structures and their self assembly, that is the vital parameter behavior for novel photochromic carbon based nanomaterials, ultimately paving the way towards new generations of responsive multifunctional nanomaterials. So, what we are trying to say that by using this kind of doped materials, by using these kind of functional materials, we can change the material properties so that the same material can enhance its optical properties or maybe the thermal properties or maybe the sensing properties or maybe the biomedical applications, so that I can use these kind of materials for the various applications and these materials will not be harmful to the environment or maybe to the human body. Thank you.